Okay. So in the last class, we tried to solve this problem. So this is a truss structure, which has 3 bars. So, and here we are considering the elastic and perfectly plastic material. So we are doing incremental analysis. This is nonlinear problem because the material behavior is not linear elastic. Okay. So in the last time, we solved the first step and then find out at the first time here the member 2 failed, right? So system is changed. So step 2. So let's consider step 2. So the result of the first step is this. Here F1, P11, P31, and P0. So now at this stage, the structure is in equilibrium. So now I'm going to increase the external load F. Then for that additional, the portion of the force, second member cannot support that additional load anymore. So only member 1 and member 3 will support that additional load. So we can think the structure system is changed, something like that, and delta F is additional load, delta P1, delta P2 is additional member force, this should be P3, delta P2 is 0. So now the system we need to analyze is that the truss, which has only 2 members. Okay? So originally we had a 3 member, and after failure of the second member, the system is changed. So for this structure, we can calculate the stiffness 0.228 and delta U, delta V, 0, delta F. Okay, here delta V, delta U. This is the equation, a linear equation we need to solve. If you compare the stiffness matrix, when we have a 3 member, the stiffness matrix is changed, right? If you compare the stiffness matrix at the step 1 and step 2, you can find out the stiffness matrix is changed. And if we solve this system, we can find delta P1 equal 0.8 delta F, delta P2 equal 0.6 delta F. So in terms of incremental force, we can calculate the incremental member force. So actual force of member 2, member 1, at the second step is a force at the first step plus delta P1. Then this become 0.5 96 P0 plus 0.8 delta F. And also member pulse of third member at the second step equal P31 plus delta P1 P3 equal P0 plus 0.6 delta F. So now we are considering only two members, member 1 and member 3. So here we need to choose which one fail. Okay, so which one has a bigger, this one, P1 has a bigger pulse, right? Member pulse. So this part is bigger than here, this part is also bigger. So here we can P1, the member, we can find out member 1 fail. Member 1 fail mean P1, 2 equal P0. So to make P1, this value is become the P0, we can find out delta F equal 0.54 P0. Okay. Then we can update all the pulses and displacement. Then we can calculate delta U equal delta V equal 1.81 EA LP0, and also we can calculate delta U and delta P1 P0 delta P2 0 delta P3 equal. So here we need to remember the member pulse of member 2 doesn't increase, so it should be 0. And all of this we can find F2 equal F1 plus delta F equal 2.25 P0, also U2, okay, V2. We can calculate V2 equal V1 plus delta V, delta V equal minus 0.6, 4.21 EA LP0, also U. We can calculate U2, P12, P22, P32. Similarly, we can calculate. So it becomes U1 plus delta U, P11 plus delta P1, P21 plus delta P2, P31 plus delta P3, something like this. So it becomes P0, P0 0.7515 P0. You become minus 0.6 EA LP0. So this is incremental procedure. So we add the incremental of poles and displacement to the result of step 1. Then we can find out the result of step 2. So at the end of step 2, member 1 and member 2 fail. So here member poles is P0. Member poles of member 1 and member 2 is P0, and member poles of P3 is smaller than P0, right? Okay. Then now let's think about step 3. Step 3, what happened? Step 3 is at end of step 2. Our situation is like this. Step 2, this is the situation. P0, right? We have only one member. So if I apply additional load, delta P1, only member 3 should support that additional load delta F, right? So now we need to solve this system. 정호, can you solve this system? We have only one bar member. Can you solve? Can you solve this system? Only one bar member positioned like this, and you pull it in this way. Huh? Huh? Yeah. So we cannot solve. So steepness matrix, steepness is singular. So we cannot solve. It means if you pull in this way, this bar rotate. So now we can find out the structural system collapse. Okay, we cannot solve anymore. So at this stage, it means collapse. Collapse already. Okay, now then, draw the graph. Okay, V, here V and F. And I'm going to normalize F with P0. And here V with the normal LP0 EA. I'm going to normalize. Okay, and then so this is a load displacement curve. So when the first member, so member 2 is failure, the displacement was 2.4 and force was 1.71. So this was a point. And then at this when second member fail, 4.21. Here, 2.25. And then this. The structure cannot support any additional load. Mean this graph. So no steepness. So this is a load displacement curve, and this is a here 2.25 mean maximum force. So collapse load. So F critical So this is a maximum. Yep. It means capacity of the structure. Capacity of the structure. Okay. So here we calculate the capacity of a structure, okay, collapse load of the structure through the incremental analysis. I know your first feeling is that incremental analysis is very complicated because we need to solve the system again and again. So in this time, we solve the system twice. But if we have a more member, for example, if we have 100 member, okay, we need to do incremental analysis maybe 10 times and 20 times. It's very complicated job, right? So some people actually, but in this graph, so people do really interested in only this value, right? People do not interested in this 1.71 and then this history, right? Load displacement history. So people really wanted to know is always the capacity of structure. This is a very important value for design of structure, right? So some people think their method, we can calculate only this value, collapse load, without this complicated analysis, and they find out some method. Okay? And the name of the analysis is a limit analysis. So the plastic limit load can be assessed without the entire history of the response. So it means without incremental analysis. So if we use limit analysis, we can calculate limit load, collapse load, without performing the complicated limit analysis. Okay, and key idea is this. In general, any structure must become a kinematic mechanism for plastic collapse to occur. So maybe you don't understand what I mean. So The second sentence means when structure collapse, rigid body mode happen. Stress structure will show some rigid body mechanism. That's here the kinematic mechanism in the motion, rigid body motion. Okay? So for example, you know this example I showed you before. So this one collapse, this one collapse. So this one yield and this one yield. Then rigid body mode will happen, right? So it means for the additional load, okay, all the energy supplied from the outside will be dissipated by bar 1, bar 2, right? It cannot be stored in member 3. You understand? You already look at the curve. Looks like this. If we have a stiffness mean structure have some ability to store the energy, deformation energy. But here there is no stiffness. It means there is no, so elastic energy cannot be stored. So first member, this member is fair. These two members can store energy, right? Then stiffness changed. At the first time, 3 members can store energy. But once the second, here this member fail, these 2 members can store energy. But if this member and this member fail, external, supplied external energy cannot be stored. So all the energy supplied to the structure should be dissipated by these 2 members. And this member doesn't stretch it, just rotate. Okay, understand? This is a very important concept to calculate the limit load using limit analysis. So now I'd like to give you example. Okay, so limit analysis is quite simple. So example. Let's consider the case we considered for the incremental analysis. So we considered 3 members, 1, 2, 3. So this is a P1, P2, P3 is a member force. So here we need to think about potential. Yeah, let's say possible for failure or collapse mechanism. Yeah. So here we have 3 members. So among these 3 members, 2 of members fail. Then this structure will collapse, right? Is that true? But now we don't know which member failed first and second, right? So let's assume like that. Then there are 3 cases. 1, member 2, okay, 1, member 2 and 3 yield. So member 2 and 3 yield, then this will fail, right? And second scenario is that member 1 and 3 yield. Third scenario is that member 1 and 2 yield. So we can make 3 different scenarios, collapse scenario, right? And let's consider case 1 first. So case 1 means here member 2 and 3 failed, and member 1 doesn't fail. Then let's calculate the externally supplied work rate. Here we need to use rate because once the structure fails, it's a dynamic phenomenon, right? So we need to consider the rate. Externally applied work rate, let's say, is equal FV, right? So this is V. So F is applied, and V is a velocity of the in direction of F. So this amount of energy will be applied, right? Per second. And internally dissipated energy. How can I calculate the internally dissipated energy? Here, only member 2 and 3 fail. Member 1 doesn't fail. So all the energy dissipation happens from member 2 and 3, right? So it will be member 2, P0, E2, plus, this is E is a stretchy, and P0, E3. That. Here, in the first scenario, E1 is 0. There is no stretch in E1 because the 2 and 3 is failed, and this is rotate. We rotate in this direction, right? So no stretch. Okay? And here we know the relation between stretch and displacement. E1 is 0.6 plus 0.8 B, E2 equal V, E3 equal minus 0.8 plus 0.6 B. We can calculate this equation from the geometry, right? So then here too. Okay, then let's continue to calculate the result. Okay, so from that equation, first of all, externally supplied work rate should be same to the internally dissipated energy, right? So WINT should be same DINT. It means FB dot equal P0 E1 E2 plus P0 E3, and this is equal P0 B dot plus P0 minus 0.8 U dot plus 0.6 V dot, right? So now we have an equation like this, right? And then here we need to consider also this condition. The member 1 doesn't stretch it. So that equation gives E1 equal 0.6 U dot plus 0.8 V dot equal 0. Now we have two conditions, right? And from here, from the second equation, we can easily calculate the relation between U and B dot, right? And if I put this result into here, finally we can find out F for the first case equal 2.667 P0. We can calculate load. Actually, this can be a critical load, 2.667 P0. Can you understand the analysis procedure? Okay. Then now let's consider the case 2. So case 2 is that member 1 and member 3 yield. So in this case, externally supplied energy rate is the same, and internally dissipated energy is P0 E1 plus P0 E3, right? Because the member 1 and 3 collapse. Member 1 and 3 yield. And using the displacement, relation between displacement and stretch, and also using the condition E2 equal 0. If I yield the externally applied energy, all the externally supplied energy is dissipated. Then we can have an equation finally, FV equal minus 0.2 P0U dot. So this is the final result. So if I look at this equation, we can easily find out we cannot solve this problem. This one doesn't give any result, right? So second case cannot happen. So cannot occur. Second case cannot happen. First case can happen, but second case cannot happen. And now let's consider third case. Third case, and external work rate is same, and internal equal P0 E1 plus P0 E2, and we need to consider E3 is 0. So E1, member 1 and member 2 fail. So in this case, if I yield then we can find out F critical load 2.25 P0. So now we, at the first time, we made 3 collapse scenario, right? And then we tested. We calculate the externally supplied work rate, and we calculate internally dissipated energy rate. Both should be same, right? And then one more equation is this kind of thing. So the member that doesn't yield should not be stretched, right? So if I use these both conditions, we can calculate critical load. So we calculate 2 critical loads. So first F1, first critical load is 2.667 P0. And critical load for third case is 2.25 P0. Which one is a real critical load? Which one? Smaller one, right? So finally, this is smaller. So critical load equal 2.25 P0. This is the same to the result of incremental analysis, right? So which analysis is easier? So do you like incremental analysis or limit analysis? Limit analysis is simpler, right? But there's a weak point of limit analysis also, right? If you do not make the possible failure scenario properly, we cannot make a good approximation of a collapse load, right? So in these cases, the collapse scenario is very easy to assume, but for very complicated structure, it's very hard to assume. Okay, so I'll give you one more example. So this is bar case and truss case. And we can do exactly the same. We can use exactly the same method for quite complicated beam structure or frame. Second example is this one. Let's say we have a beam frame structure like this. Here, this part is hinged, this part is fixed. So, dimension 2L, here, L, L, and there are load F applied here, 2F applied here. So we wanted to calculate the collapse load F. And let's say the cross section of these three beams are same, and plastic moment equal M0 for the all three member. Okay? So first time we need to consider how this structure fail. Okay, there we can make a lot of scenario, right? Almost infinite number of scenario, right? So one of the scenario is that something like this. Let's consider the first scenario. Put the possible collapse mechanism is this. Here we have a plastic moment happen here, and the other plastic moment appear here, and the other collapse here. So once this structure have three plastic hinge, this will fail, right? So here 2F, here F. And let's say this is theta. And so of course this should be 2 theta. And from here to here is V. This is a first scenario we can assume. Then externally applied supplied energy equal F 2F V dot, right? Very simple, because F is applied here, V is this. But the here lateral force F doesn't give any work because no displacement at this point, right? And how about the internal dissipation? So we have three plastic hinge, right? First plastic hinge dissipate energy amount is that M0 and zeta dot, right? M0 zeta dot. Because at this point, the rotation of two member is zeta, right? And plus, how about second hinge? Moment plus 2 zeta dot, right? And third hinge plus M0 just zeta dot. And also, we can easily find the relation between V and zeta. Zeta equal, so from here to here, L over V, right? Or B equal L zeta from the geometry. And then externally applied energy should be same. All the externally applied should be dissipated. Then this will give us the critical load Fi equal 2Lm0. Okay. Calculation is very simple in this case also, right? Okay. Then similarly we can consider other collapse scenario. For example, this collapse scenario. So we have a plot hinge as D3 point, and this is zeta, and this is U, and 2F, here F is applied. And third scenario is that a little bit more complicated. Okay. And fourth scenario. Something like this. We can assume this kind of scenario. So here, zeta, this will be 2 zeta, here 2 zeta, zeta, 2 zeta, 2 zeta, something like that. And calculation procedure is exactly similar. So in this case, F2 equals 3 to L M0, F3 4, 5 L M0. Actually, cannot occur. So, if I consider this 4 case, which one is the most possible collapse load? Most possible. It's the smallest one, right? Which one is the smallest one? Smallest one is, this is smallest one. But if we consider more other different case, we can calculate, okay, smaller one than this. It's possible, right? So, if we use limit analysis, we can calculate always upper bound of the collapse load. Okay? Upper bound. And then among all the upper bound, the minimum one will be a exact collapse load. Okay? Okay, so I need to finish.